Hi everyone, I'm Chi and I'm a final year PhD student in the Terahertz Applications Group at the University of Cambridge. Welcome to my talk today about new insights into the crystallographic disorder in the polymorphic forms of aspirin from low-frequency vibrational analysis. Here is a brief outline for today's talk. I will start with a brief introduction, and then I will show you our experimental and computational methods for this project. And then I will show you the results and discussions we achieved, and end with a short conclusion. So now on top left, we can see the molecular structure of aspirin, and the bottom, you're probably going to be familiar with this as you can get aspirin pellets from any pharmacy. So the aspirin form 1 was first characterized in 1964 by Whitley, and then a long time there were discussions like there might be another form 2, that is also stable for aspirin. And not until 2005 there been solid evidence of the existence of aspirin form 2. And in 2010, Bond discovered a method that can reproducibly synthesize aspirin form 2 in the presence of aspirin anhydride during the synthesis process. And even until recently, there are more new polymorphs of aspirin are discovered. But for our talk today, we're going to mainly focus on the two polymorphs of aspirin. Aspirin form 1 showing on the left side right now, and form 2 showing on the right side. So here's the projections from A, B, C axis for both polymorphs. And as you can see, they look very similar from the B and C axis, while you can notice some difference from when you project from the A axis. That's it seems the layer is shifting about half a length along the C-axis. So that's the only difference between the aspirin form 1 and form 2. So we're going to look at those two very highly similar polymorphs. So for our project today, we're mainly applied the Terahertz time spectroscopy to investigate the two polymorphs. For some of you might not be very familiar with Terahertz spectroscopy. Some background is the Terahertz radiation is located between the far infrared and the microwave region, and because of this region, its low frequency region, it is very sensitive to both inter and intramolecular motions. So it can probe all the collective motions in the crystalline lattice, which make it very sensitive to slight change of the structure, and it's very useful to study polymorphs, as in the aspirin case. On the left corner here is just short video as an example to show the collective motions that can be probed with the Terahertz spectroscopy. So as you can see, it's not like a single bond stretching or group rotation, but it's more like the whole structure and all the atoms are moving somehow. So that's the complex motion we're gonna look in the later of the results and discussions. Well, because of the motions in the Terahertz region is very complex, so we cannot fully interpret the spectral results directly from the experimental results. So we need help from some computational method. For our project, we use the density functional theory calculations, and the two main assumptions for DFT is all the calculations are performed at 0K, and the atoms are assumed to move harmonically. And for our project, we used the Crystal 17 software package to perform all the calculations. And now let's start the results and discussion part. At bottom, it shows a reference. So we used the method described in that paper to synthesize our aspirin form 2 sample for this project. And when we acquired the Terahertz spectrum, we actually mixed the aspirin sample either form 1 or form 2 with polyethylene to a weight concentration about 5%. And then we compact the mixed powder into a pellet and place into our optical chamber to acquire the Terahertz spectrum. Here now shows on the left side in the figure, it shows two sample of the form 2 and one for form 1. So the form 1 we just used as received. It's a commercial sample from Sigma Aldrich, while the form 2 we synthesized it, but we previously categorized it with XRD to study the purity. And from the XRD result, it's not showing here, but we see the red one has a relatively high purity, while the yellow one has a relatively low purity. But no matter what, three of them shows very similar spectral shape. So what we did next is we normalized the three spectrum relatively to the feature at 1.8 terahertz. What's the reason of that? We're going to explain it later, but for now, as you can see, even though it looks very similar before that, now you can actually spot three obvious differences between the spectrum of form 2 and form 1 now. So first of all, there's the feature at just about 1.5 terahertz seems more intense for form 2 than for form 1, and also the feature just below 2 terahertz, it seems the feature over there is broader for form 2 than for form 1. And also the right shoulder after the feature at 2.4 terahertz, it seems the right shoulder is higher for form 2 than for form 1. So to fully understand the spectrum of both form 1 and form 2, we then did our DFT calculations. So first of all, we optimized the structures with the PBED3 density functional and the LRIX VTZ with polarization basis set, and then we calculated the spectra of both forms. First of all, let's start with some physical properties that we calculated from our simulations. All the properties you can see, they are very comparable between form 1 and form 2. So the form 1 has slightly lower total energy than form 2, which also reflects it might be more stable than form 2. But all the other, like volume, density, cohesive energy, they're very close to each other. And we can also see the form 2 has a slightly higher vibrational entropy than form 1, which might also reflect it's more disordered in nature. And after that, we can actually compare our calculated spectrum with our experimental spectrum. So here, the blue spectra represent experimental results, while the black and the gray curve represent our simulated spectrum. And the solid line for form 1, while the dashed lines are for form 2. As you can see here, they actually matched pretty well. And now we can explain why we normalized the experimental results relatively to feature at 1.8 terahertz. So if you see the simulated spectrum of both form 1 and form 2, that the feature at 1.8 are predicted in both forms, and also the intensities are very similar. So that's why we chose that feature to normalize relative to that feature, so we don't change the experimental result. And then we plot the simulated spectra of both form 1 and form 2, and the bandwidth was set to 1 wave numbers to show almost every feature we predicted. And as you can see here, we can actually explain the three differences. So the feature at 1.5 terahertz actually only predicted for form 2, not in form 1. So that explains why it seems more intense in our experimental result for form 2. And also there's an extra feature predicted for form 2 just below 2 terahertz, which might lift, and it looks like the feature just below 2 terahertz is more broader in experimental result. And the third, there is a feature predicting form 2 above 2.5 terahertz. That might cost, so due to the temperature difference and also our calculated at 0K, it might shift it to relatively lower frequency in our experimental result, which can be used to explain the relatively higher right shoulder in the form 2 than in form 1. And then what we did next is we fitted our experimental spectrum with the predicted modes from our computational results. And equations are shown here. So the first term is the Lorentzian fitting to fit each peaks on our spectrum data. And then the BA times x to the power of a plus c is to fit the baseline using a power law. So then here we show how our method fit with our experimental data. You can see it fits really well, and the major fitting parameters are showing in the table at the bottom. So the main information here is that you can see the fitting parameters for form 1 are generally magnitude lower than the fitting parameters for form 2, which reflects the more disordered of form 2 and form 1. But also the form 1, we used the sample as received, while the form 2, we synthesized it. So it also can be explained by the relatively higher purity of form 1. The two tables here shows the fitted of each features on the spectrum, and the highlighted modes shows the one that's predicted in the other form rather than the current one. For example, on the left side, the highlighted 1.53 terahertz is the modes predicted for form 2, while the table is showing the fitting data for form 1, same as the second table. But as you can see here, we have to use some modes from the other form to perfectly fit our experimental data. That's also evidence that there's some intergrowns in the both polymorphs. So there's some form 2 in the form 1 and form 1 domain in the form 2. That's so here the table gives our confidence to give the idea of the intergrowns of the two polymorphs. And what we also spotted from our calculated spectrum is that here shows the two modes, that the left one is for form 1 and the right one is for form 2. They're relatively at the same frequency, but if you looking close to the highlighted methyl group, you can see that the methyl group moves freely and in a larger amplitude in form 2 rather than in form 1. And this phenomenon is consistent in almost the whole frequency range of our interest. And to look into that part more, we actually measure distance between the hydrogen on the methyl group to the nearest aspirin molecules of both in form 1 and form 2. And you can see that the distance is slightly larger in all different directions in form 2 than in form 1. And don't think that's because of the volume difference, because we have checked that the form 1 actually have a larger volume than form 2. So even if that's the case, the different distance between the hydrogen to the nearest aspirin influence the behavior of the methyl group in the aspirin. And this has also been reported previously in one of the released papers in 2014. And here I have showed all the results we got from the aspirin project, and we used the Terahertz time domain spectroscopy and the density function simulations to study the two highly similar polymorphs of aspirin. But we also show, like, even though their structure are very similar, they actually show clear spectral differences in the Terahertz region. And we also proved the integrals of their nature. And also we can, by comparing the calculated physical properties of the two polymorphs, we can prove the structural similarities, but also the form 2 is predicted to have a higher or larger vibration entropy than form 1. For the future work, if we really have enough computational resources, it would be really nice if we can do some simulations on a supercell structure with defects, so we can bring more insights to the phase transition that might be triggered by the defects between the two polymorphs. And thanks to everyone to the Terahertz group and my funding buddy CSC, and also Archer for supporting our computational work. And thank you for your attention.